Nothing beats more math, more videos. This is a video we're gonna continue investigating infinite limits, and specifically we're gonna focus on the concept of a vertical asymptote. So let's take a look at what this is all about. All right, first of all, let's define a vertical asymptote. The definition of a vertical asymptote right here is, we say a vertical line. Let's call it x is equal to a. X is equal to some real number. This is called a vertical asymptote of the function y is f of x if any of the following are going to be true. Any of them. Even one of them, that's enough for that to be true. For a vertical line, x is equal to a, to be a vertical asymptote of a function. Okay, so keep that in mind. We only need one of these to be true, but multiple things could be true simultaneously. First thing is, let's consider a function f of x right up here. Here's the notation. Limit as x goes to a from the right of this function f of x is infinity. So as we can see in the picture, here is this vertical line. X is a, right? Vertical line up and down. And as I'm approaching a in the x direction from the right, the function is going straight up to infinity, getting infinitely big without bound, but never actually reaching x is equal to a. So that can happen. If that happens, then x is equals to a is vertical asymptote for the function f of x. Or you say a little or, but what else? Well, what if the kind of same thing happens as the previous situation, except now I'm letting x approach a from the left of the function, now f of x, and the function is growing without bound towards positive infinity. Okay, as we can see in the picture again, this time x is approaching a from the left of a. We see the vertical line x is equal to a here, and the function is going straight up to infinity. So if that happens, then the vertical line x is equal to a is a vertical asymptote for the function f of x. So basically, the first two cases here, right, to summarize, if x is approaching some number, some real number a from the left or the right, and the function is blowing up towards infinity, then x is equal to a, that vertical line, is a vertical asymptote of the function f of x. So in these next two cases, still, any of these things, any of them, if they happen, we got a vertical asymptote x is equal to a. And now what we see in this situation is that we're going to approach x is a from the right again of the function f of x in our picture, but instead of going to positive infinity, the function is approaching negative infinity. And so again, in the picture, x is equal to a, this vertical line right here, we can see as x approaches a from the right, the function itself is approaching negative infinity now, right? So it's going towards negative infinity direction. It's growing with magnitude without bound, but in the negative direction. If that happens, x is equal to a is a vertical asymptote for the function f of x. And one last situation here, might have thought this was the case. Now, as x is approaching a from the left of the function f of x, if that function is approaching now negative infinity, then again, the vertical line x is equal to a here is called a vertical asymptote for the function f of x. So in this case, we see x is approaching a from the left, and the function is approaching negative infinity. Again, keeping in mind, when any of these situations happen, the limit as x approaches a from really either direction, both directions as well, doesn't exist. However, we can use the notation here to give us some meaning behind what's actually going on in the situation. But again, any of those four things happen, then you have that x is equal to a is a vertical asymptote for the function f of x. That vertical line x is equal to a. So, in other words, summary, x approaches a from the left or the right. If either direction, the function is either blowing up towards infinity or negative infinity, then the function f of x has a vertical asymptote x equals to a. The vertical line x is a. So that's how we define it. Those are the different situations. Multiple situations can happen at once. Let's take a look at a few examples here to wrap up the video to get an idea. That's what I'm saying. Let's look at a few functions and their graphs with some initial examples on vertical asymptotes. So here is a function. We see the function f of x here defined on the left, the rule, and then we have, of course, the graph given to us. So what is this function? Well, that first statement is piecewise, as we can see. If the function is non-zero, if the value of x is non-zero, then the function is going to behave like the elementary reciprocal function 1 divided by x. And that's where we see basically the graph there. It mostly looks like 1 divided by x, right? However, 1 over x is not defined at 0 in general, and in this case 2. If x is 0, then the function is defined to be 2. There's that little dot right there in the picture, right? Oh, x is 0, then the function actually happens to be 2. Now, even though the function is defined here, don't really play a role, because the whole point of this is to show that in this situation, notice that limit as x approaches 0 from the left of this function f of x is negative infinity. That's that behavior right there, right? We're approaching 0 from the left. The function is going down towards negative infinity. That alone is enough to say that x is equal to 0 is a vertical asymptote of the function f of x. That vertical line, so basically that's the y-axis in this picture, right? That line right there, boom, just tracing it in, just so you see it. But that vertical line is a vertical asymptote for this function f of x for that reason. Now, it's not the only reason that x is equal to 0 is a vertical asymptote for this function. Also note that as x approaches 0 from the right, the function approaches infinity. So right up here, we could write limit x goes to 0 from the right of the function f of x is infinity, right? Going to 0 from the right, function's going up to infinity. So that's also a reason. So both of them are reasons to give that x equals to 0 is a vertical asymptote of the function here. But we actually have two different situations happening at the same time, which definitely could take place, but all we need is one of them. And note, too, the function is defined at 0, right? It's 2. That's that dot. That's the whole purpose of this, to show that, hey, that's kind of a weird situation, but we can define a function that behaves such a way. How about another function? Let's take another look. Got a couple more examples just to see it real quick. In this case, g of x, logarithm of base 1/2 of x minus 1. Graph, as you can see right there on the screen. There it is. Now, in this case, understanding the behavior of logarithms, we know that this function g of x is defined for x bigger than 1. And that's why you don't see no graph on the left of 1 there, because it's not defined, nor is it defined at x is 1. However, logarithms do have vertical asymptotes. And in this case, we can see in the graph over here that the limit as x approaches 1 from the right of g of x is positive infinity. Approaching 1 from the right, function going up to infinity. Even though it's not defined to the left of x is 1 or at 1, this limit happens, and hence x is equal to 1 is the vertical asymptote, spell that real quick, of the function g of x. Because all we need is one of those things to happen like we talked about before. So that's an example. And then finally, the last example is one where, hey, you know what? There are functions that exist that have infinitely many vertical asymptotes, including our elementary tangent function here. H of x is tangent of x. So I've just shown a little graph here of some of them. Clearly, it goes on like this forever in the negative and positive directions. But this is a case where we have infinitely many, right? Because, of course, tangent function is defined to be the sine function over the cosine function. Then whenever we have a value of x that makes the cosine function 0, and it ends up the sine of that same value is also non-zero in this case, we produce the vertical asymptotes here. So you might think, well, okay, there's like infinitely many different behaviors that are happening, but there are patterns. You say, what are the vertical asymptotes? So vertical asymptotes here, all these infinitely many vertical lines for which the function is approaching infinity or negative infinity in different directions. Well, those are all going to be the lines where x is equal to, say, pi over 2. Notice that obviously right here at pi over 2 we have a vertical asymptote, because as x approaches pi over 2 from the left, the function goes to infinity, and as x goes to pi over 2 from the right, the function goes to negative infinity. So that's one of them. And then, of course, the period of a tangent function is pi units, right? So there's pi units between all these things, etc. So we could say plus some pi times some number k, where k is an integer. Remember that z-looking symbol right there just means an integer value, positive and negative whole numbers, including 0. So you just add or subtract multiples of k from pi over 2, and you will be at a vertical asymptote because of the behavior of the function. And we could even go further and describe all infinitely many different behaviors of all these asymptotes if we needed to. But the point I think I'm trying to make here is that, you know, this function tangent of x has infinitely many situations for which we have vertical asymptotes, whereas functions that we showed in prior examples right now, there happen to be 1 or 2 or whatever. And so really anything can happen with these functions in terms of vertical asymptotes, as long as it satisfies the criteria that we've been given, like we've stated earlier on in the video. So hopefully that gives you a general idea of like what it means to be a vertical asymptote, right? How we define it by using limits that go to infinity or negative infinity as x approaches a real number from the left or right. If that happens, then x is equal to a as a vertical asymptote with the function. And so we got a few more things to talk about still with limits involving infinity. And so that's what we'll focus in the sequence of videos right now. So until then, it's Matt and Bates, and I'm out. Later.